Thank you, Merce, for that kind introduction, and to EPFL. Once more, happy birthday, and for inviting me. It's my first time in Switzerland, and I am thoroughly enjoying your beautiful country. I want to start by thanking my co-author in the development of all of these ideas. We've been working together, Lindsay Hagee, a geophysicist who works with me, and a lot of this has been really done hand in hand. I swear that I did not coordinate my talk with Jeanette, but I think you're going to hear a lot of echoes of our ideas in here, and I think there's good reason for that, because I think this is a really a central concern for those of us who are trying to build sort of data science as this new endeavor. And I want to focus specifically on the role that software tools play in that space. I also didn't coordinate with Martin or anyone else, but it seems that every talk has to have a pyramid, so this is my pyramid. And the point that we're trying to make here is that when we talk about open source software, the word software takes prominence, and immediately our minds go to GitHub, to code, to programming languages. And actually, I want to de-emphasize the software part and talk about the rest of the story, because that's where the complexity is, and I think that's where a lot of the value resides. And so software, yes, we write code, but it supports actually something more. It supports content and services. Specifically, I want to talk about Project Jupyter. For those of us who don't know what it is, Jupyter is a project that evolved out of something smaller that was called IPython and that still exists, and it's kind of an expansion of the ideas in IPython, and it's basically a set of tools for what we call interactive computing, which at heart is a very simple endeavor. Write a little bit of programming code, like in that central image or on the left, and get the answer back, maybe plot some data, view something, and keep iterating in that process. Very simple idea. It's been around in computing for a long time, but that workflow is central to science, and it's different from writing software, say, in industry against a well-defined specification, because the point is the scientist is using the computer as a tool to think, as a tool to explore data, an algorithm, a question, and so you need to allow the problem to kind of change under your eyes. You need your understanding to evolve. You need to have a conversation between yourself and the computer and the problem. And this is what these tools are designed for. The probably most well-known part of the Jupyter ecosystem is at the center. It's called the Jupyter Notebook. This idea of computational notebooks is not something that we invented in Jupyter. It's been around for a long time. Systems like Maple and Mathematica have had it for a long time. And the idea is to build documents that combine this computational narrative, if you will, of code and the results from that code stored in a document, but combined with natural language, where you actually put English, French, Spanish, the language of your choice, and potentially mathematics, and you build a document that weaves two threads together. The thread of natural language, the story you're telling, and the thread of computation that goes along. And the point is, yes, we've written code to do that, but what really has brought impact out to the world are the stories that people tell with that, the problems they look at, how they can share with others what they've done, and that is embodied into services that we actually run to facilitate the sharing of those things. And that's not writing code. That's a different level. Below the code, we've actually, in Project Jupyter, taken a step back and said, these things that we're doing are actually generic ideas that we should allow others to implement. Maybe others will do something with them better than us. Maybe others will do something different. And so let's actually take a moment to standardize them, to define them as open protocols, to work with an open community, to refine these ideas as generic ideas for other use cases. That takes a lot of effort and has nothing to do with the actual code. But by doing that, the project that began in the Python world, IPython, then could support a programming language called Julia that some of you may know, and then it could support R that Jeanette was referring to earlier, widely used in the statistics world. And basically this idea of a protocol for interactive computation became adopted by many programming languages, and today there's support for over 100 different ones. And we basically have been able to support the growth of an ecosystem of interoperable tools around interactive computing, all of which benefit from the Jupyter machinery, and where the authors from all of those communities don't have to write the millions of lines of code and build all the systems we've built. They just need to concentrate on this one protocol. But even these ideas don't happen in a vacuum. They happen by people. People do these things. And people means communities. It means communities that need to be managed, that need to be supported, communities that have stakeholders of very different kinds and types and with different interests and needs and career paths. They need to be governed. And in Project Jupiter, we've put a lot of effort into figuring this out. So the project today is co-directed by Brian Granger and myself. Brian is actually a friend from grad school, a physics professor at at Cal Poly in San Luis Obispo, and actually right now, as Jeanette was mentioning, interesting forms of partnership. He's now at Amazon. We have a formal steering council for the project made up of roughly 15 people. That helps us define how we interact with institutions like companies or universities or labs that may employ people, with sponsors who may fund our work. We are connected to a nonprofit foundation called NumFocus that provides effectively nonprofit status to open source projects. So this is a pretty elaborate system, and it's actually under complete revamping right now, because as elaborate as it is, it isn't quite sufficient. The project has evolved to a level where even the governance model that we have is kind of creaky and failing to really give us what we need. So the point is, the code is only a small part. The stories on top of the code are what drive impact in the world. The expression of the underlying ideas and taking the time to express those ideas in ways that others can use is what allows for the growth of an actual open, interoperable ecosystem. And the fostering, which is not automatic, it takes a hell of a lot of work, but the fostering of a community of people who wants to work and wants to collaborate on these ideas is precisely what gives you new sources of innovation, new sources of ideas, and resiliency, because this diversity of stakeholders, this tapestry of people working on this actually provides resiliency against kind of single points of failure that might be possible under more traditional models. So if we think of it this way, open source software is a lot more than software, right? And I believe that it can now play a role in supporting science, which is not just open, but that actually is a little bit more than open. And this is a bit of a nod to the FAIR principles of open data. I think we should think about science not just in terms of openness, but actually in terms of collaboration, reproducibility, and extensibility as principles that actually work together. What do I mean by collaborative, and what do we do in that regard? Well, as I said, we have a big community of stakeholders that actually come from multiple walks of life, right? We have people like myself who are in academia. I'm now faculty and therefore subject to the constraints of faculty. We have folks who work, for example, with these tools in education at the high school level, right? And those needs are very different from ours. There are folks from multiple companies. This is a picture from one of our most recent sort of team developer meeting, and in that picture there are folks who either now or before have worked at IBM, Google, Bloomberg, Netflix, not in this picture, but there were, in the previous meeting there were folks from Netflix, Bloomberg, let's see, Quansight, company in Sweden whose name I don't recall. There are government lab scientists. There are, not in this picture, but we have in the community folks from media and journalism who are using these tools to basically communicate and interpret, as Jeanette was saying, interpret the data. Actually, a professor from Columbia did a beautiful study that some of you may have seen a couple of, I think it was about a year ago, that made a lot of noise in the New York Times, who discovered the use of massive bot networks by Twitter and Facebook, right? And that led to the deletion of millions and millions of accounts by these companies. All of those analyses were done using the Jupyter machinery. The underlying data analysis was done using Jupyter. So all of these stakeholders have extremely different constraints, and they operate against very different sets of incentives. How do you make them work effectively and connect them to this diffuse community of volunteers who work maybe nights and weekends, who at any given time may do small amounts of work, though some of them do a lot, but who in the aggregate are absolutely critical to the success of a project like this? It also means collaborating across disciplines, right? So Jeanette was referring to the issues of funding from the federal agencies and mentioned Pangeo. Well, this is a new success story that we're very proud of. Together, Ryan Abernathy, the lead of Pangeo, was not on this grant, but Joe Hammond, who is his co-PI at NCAR, together with Laurel Larson, who's a hydrologist at UC Berkeley, Kevin Paul at NCAR, and myself, and Lindsay, who actually led a lot of the writing of the grant, we actually got the NSF to fund the development of something that was unapologetically both software and science, right? We didn't say, we're going to do science and publish a lot of paper, wink, wink, nod, nod, don't look here, we're going to write some code. Neither did we say, this is a scientific computing infrastructure project where we will build blah, 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 and we might talk to some scientists. No, we said science and software need to be partners on equal footing, both respected, and the NSF needs to pay for both. And they need to be treated as equal partners. So this is the kind of collaboration that can be supported with these approaches. We just got the funding recently. We're beginning to kind of set up the hires, but we're very excited about this idea of driving tech development in close partnership with 3 specific use cases in the geosciences. The word open is a very overloaded word. It is a word that has been explored by many of us here, so I won't dwell too much on it, but we can talk about code in terms of licensing and the legal implications about data, but also about access to publications, and not just publications. I want to use the word artifacts because I think we are thinking well beyond the PDF in that sense, and what are the actual artifacts of research. But also, as I've mentioned, the openness of standards that support interoperability and of a community where all are actually genuinely welcome, and that's something that you need to work on. You don't just say we have an open community. You actually have to do a lot of very intentional work for that to be true. Now, the R is about reproducibility, and we've talked already and we've mentioned issues of reproducibility, but one point that I want to make is that reproducibility is important as an aspect of publication, but I think it's important to flag that it is also the engine of collaboration. We shouldn't think about reproducibility just so that the papers are reproducible, but rather that if we adopt practices that are more reproducible, as we do our work, and if we do it openly, then the process of science is one that supports collaboration. And there's one specific piece of the Jupyter ecosystem that tries to be our contribution to this problem, and this is something where Switzerland is making a major contribution. Tim Head, who's here in the audience, is one of the lead contributors in this project. The idea behind Binder is basically to say, using the Jupyter machinery, asking if a scientist has put their work on GitHub or another basically publicly available repository and their code is available, and importantly, explicitly says, these are the dependencies of my code, right? This is my work, this is my analysis, and my code is available here, and this is what the code needs to run. And you have to say that, right? You can't, you have to tell us what your dependencies are. Then what the service provides is a very simple web page where you can put a link, you provide a URL that says, here's my code, and I've done that. And out comes something that uses the magic of Docker and Kubernetes and the cloud and blah, 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 pixie dust, and magically a URL comes back that says, here, run it. So in comes a URL, here's my code, out comes a URL that says here, run it, and you can share that and you can give it to others so that they can actually execute, build on what you just did. This is an example that made us very proud. I'm a recovered particle physicist by training, and so I was very proud, along with the rest of the team, that in 2015, some of you may have seen that something went kind of beep in the night, and about 1.3 billion light years away from us, 2 black holes merged into one another. The detection of that event led to the 2017 Nobel Prize in Physics. That's the first figure on the paper from that original discovery. That entire paper was made with open source software, right? That was NumPy, SciPy, Matplotlib, etc. That was a huge source of pride for those of us who have spent 20 years building these tools with people telling us that we shouldn't, that this wasn't real work. And then that paper is actually generated from code, Python code, that any of you can go to that URL, click on, and you get a binder. You get one of these things that lets you run it, and you'll get to that. Again. That, whoop, is that last 0.25 seconds when roughly, I think, 26, 29 solar masses in 2 black holes spiraled into one another. They merged, and they ejected about 3 solar masses worth of gravitational wave energy, which we picked up on the night of September 14, 2015. And anyone with a web browser can click on it and actually run that code and play it. And I think that's really cool. But it's not just reproducibility in the black box sense of push the button and out comes the clown. It's actually build on it, make the clown do something different, right? And so we want these tools to be extensible, tools that others can build upon. For the last few years, we've worked on taking the core ideas in Jupyter and interactivity and actually decomposing them and recomposing them for the community as a toolkit that can be assembled. It's called Jupyter Lab. It came out earlier this year. It was a huge team effort in a collaboration between industry and open source developers that still provides the same basic ideas of notebooks, et cetera, that we've had for a long time, and I don't have time to get into all the details. The point that I want to make, and this was not in coordination with Jeanette, but it came from a visit to Columbia a few months ago. This is work from Aurel Lazar, a PI at Columbia, whose team took Jupyter Lab and built FlyBrain Lab. They're neuroscientists who study fruit flies and the brain of fruit flies. And they built this. It's a heavily customized Jupyter Lab where they can talk to their database of fruit fly data, open a 3D viewer that shows the anatomy. For each of those circuits, they can get the electrical circuit representation corresponding to the anatomical circuit, run a simulation on a GPU cluster, get the genomics data associated with it. All of these are plugins that they have built that drop into the existing Jupyter Lab machinery to get basically a heavily domain-specific scientific interface for their needs built upon the generic framework that we put out there. And as I was boarding my plane, literally at the airport lounge, I took the screenshot, and I'm going to get to meet the team here at EPFL that similarly took Jupyter Lab to build Noto, and I can't tell you too much more about it because I don't know yet. I need to talk to them, but Noto is apparently the EPFL platform using Jupyter Lab for research and education here. And finally, infrastructure is not, so it's not just Switzerland that is doing this. Canada is actually deploying this nationwide. So in Canada, the Pacific Institute for Mathematical Sciences, which is at UBC, PIMS, together with Cybera and Compute Canada, have deployed two projects. One is called Callisto, and what Callisto offers is Jupyter deployments for K-12 education together with curricular development for the entire, it began as an Alberta project, but I think in September they extended to all of Canada. And Syzygy is a project that gives Jupyter hosted on HPC facilities for Canadian researchers. So basically at this point in Canada, they're deploying Jupyter resources on national infrastructure from kindergarten to supercomputers. I think that's cool, and that is the value of these open, extensible tools that others can adopt and repurpose. Industry has also taken these things. So at this point, I won't go into the details, but basically all of the big tech players, Microsoft, Google, Amazon, IBM, et cetera, they all have products based on Jupyter in one form or another, and products with paying customers. And with these tools, we are having impact in research and education. At UC Berkeley, if any of you has ever been to campus and has gone to the Performing Arts Complex, you may recognize that that's not a classroom, that's Zellerbach Hall, that's our opera hall on campus. That's the first day of classes for our Foundations of Data Science course. It doesn't fit in any classroom on campus. We need to basically borrow from campus. The opera hall, we have about 50, this picture had about 1,300 students. I think the current numbers are closer to 1,500 or more. This is a course that is reaching, is the low-level foundation that is reaching basically roughly 50% of campus at this point is taking this class. And it's made possible, it lets us bring to the freshman level, first semester students from any major ideas in computation and data because we have this open infrastructure deployed in the cloud that lowers economic barriers because if a student doesn't have a fancy laptop, they go to the library, they check out a Chromebook and they can do their homework regardless of the resources they have personally. Faculty can contribute and get courses running on this platform without themselves being cloud engineers. And that course is actually followed by a sequence of other courses. I'm currently teaching Data 102 with Mike Jordan, which is the fourth one in that sequence, and an entire constellation of courses that kind of attach to that backbone made of Data 8 and these other three, and that constitute an entire, not just a major, but actually a system of courses in data science that is actually really having a huge educational impact at UC Berkeley. And in research, I will not steal the thunder of our next speaker, but I was incredibly proud and grateful that Dr. Katie Bauman and her team actually, in their observation of this black hole with the Event Horizon Telescope project, actually cited NumPy, SciPy, Pandas, AstroPy, Jupyter, and Matplotlib in their paper. Jeanette was referring to the problem of software being considered real work in science. That was kind of the story of my life, and being actually recognized by a team that made such an amazing contribution to science is really valuable and important. I have a picture of Shep Doleman, her colleague, from giving one of the first public talks at Berkeley in April. I don't have a picture of her because I made it to her talk, but it was, even though I showed up half an hour early, the auditorium was so overcrowded that they kicked me out of the room because I was sitting in the stairs. So today I'm finally going to actually see her in action. I had to watch it from the overflow screens outside, together with like a couple hundred people who got kicked out of the room. But we're absolutely delighted that we are contributing not just to basic education, but actually to cutting-edge research, like the discovery of gravitational waves and the observation of black holes. But it's great, right? We're having all these successes. We're in academia. I'm faculty at UC Berkeley. We've gotten grants from all the big foundations, from the NSF, from the Department of Energy, support from virtually every tech company in the world. What's not to like? So William Stein is a mathematics professor at UW, fully tenured. He actually had tenured offers when he left Harvard as a postdoc straight out. He's the creator of SAGE, which is a system based on Python for mathematical research. In fact, it had kind of the first really well-functioning version of a web-based notebook for these things came from SAGE, and we took a lot of ideas from them. He's trying to sustain SAGE. Started a company, took a leave of absence from campus. How do I do this in academia? And this rather kind of heartbreaking blog post came from William a few months ago, where eventually he said, you know what, I can't do this. This is a fully tenured professor, very successful number theorist, extremely well recognized in his field, who basically said, I give up. This does not work. This isn't doable. I could go on with many, many more stories like this. I'm just giving this one out for reference. Because the problem is there's a very, very problematic tension between how academia functions and how these open projects operate. Just across every dimension you can think of, the incentive structure, what is recognized, what is supported, what is allowed, is fundamentally different between the two. And so if we're saying that these tools are central to research, these tensions are going to have to be resolved somehow. And each of them is probably the topic for a complicated conversation. I just want to leave it out there for thought. But in the words of Tracy Teal, the director of the Carpentries Project, we are the victims of catastrophic success. In 2015, people looked at the data, the citation data in astronomy, to ask the question, is IDL, which is a programming language heavily used in astronomy, still the dominant tool or not? And they said, come 2015, Python has taken over IDL. In 2015, basically, IDL is now the second-rate player, and those curves, once they cross, they don't go back. But if you look at IDL or MATLAB or Mathematica, each of these companies has hundreds or thousands of employees. Those people do real work. Those people develop software. Those people write documentation. They develop, they fix bugs. They support a community of users, right? If we replace all those people and these tools, now those tools are proprietary, and I would rather have science be done with open tools that we can inspect, that we can reuse, that we can share, that we can understand, that anyone in the world can use regardless of their economic conditions, which is not true of these proprietary tools. So I'm all for replacing them with and basically I've made, the last 20 years of my life have been a battle to have open tools that are a viable replacement for proprietary ones. But those people did real useful work. I'm not demonizing those people. What do we do if we are going to build science on top of these other things? Who's going to do that work and how? So those are some of the questions that I think we should think about. I want to thank, in addition to the broader Jupyter community, my local team in the Bay Area, all the people that I've worked with in the past or now, both at LBL and UC Berkeley, and even the Bloomberg team that we collaborate closely with. And I want to leave with these questions that I think we need to tackle. If we're going to avoid a form of collapse of this ecosystem around these open tools, we're going to have to understand how to square the circle of incentives and sustainability. We're going to have to think about the problem of governance of these projects that cut across academia, industry, community, etc. Jeanette made very, very good points about the problem of career paths and professional roles, how to build these organizations. None of us trained for this, right? Guess how many courses on any of this I had while I was doing a PhD in particle physics? 0, right? And most of you who are trained as academic scientists have no knowledge of these problems. But these are some of the challenges that we need to figure out. There are communities who study these questions, and I hope that together and meeting with the experts, we actually come up with a combination of community norms, new ideas, new models, policy changes to make progress on this. And I'd love to talk to you more about it. Thank you very much for your attention.